Okay, so when we've looked at the min terms and max terms, those were the canonical forms. Let's see here. Sum of min terms and product of max terms. Those are canonical form. Now, you've seen these are pretty robust expressions, lots of terms and all that sort of stuff. These are typically not the reduced forms that are implemented in circuitry. Those typically are going to be the standard forms. Which is the sum of products and the product of sums. So while the sum of min terms expression might be something like this. It's a sum of min terms, and a min term has all the literals in each min term. So if there are three literals, every and function and operation is going to have three literals in it. Whereas, let's see if we can reduce this here. X prime, X, Y, Z, Z prime plus X prime Z, Y plus Y prime. Yeah, that should be, that's proper use of the distributive property, right? Distributive law. Does that look right? Distribute out the X and Z from these two, X prime and Z from these two, and left with that, and that further reduces to X, Y, Z prime plus X prime Z, because this is 1. Y ORed with its complement is going to be 1. And when you AND 1 with something, it remains the same, so you can drop the 1 from here. This is the canonical form. This is the standard form. As you can see, it has fewer literals, fewer gates, That's a sum of products. When you're using a standard form, whether it's the sum of products or a product of sums, what you're creating is what is called a two-level structure of gates. Because you have, in this case here, x, y, z prime, and x, z prime, and you have it's just two levels. This is more preferred than a 3 or 4 level implementation because of the time it takes to get to propagate from the input. Oh, this wasn't prime; it was x prime. Yeah. The time it takes for the input to propagate to the output is minimized. Add another layer of gates, and it slows it down. And speed is of the utmost importance when it comes to digital logic. So you want to stick to the standard forms for implementation. Let's see here. Gives an example of a let me go ahead and erase these. Let's see here. A, B, C, D, E. And this is going to go a AND gate. Bless you. OR gate. AND gate. And then OR gate. See, this is a 3-level implementation. The expression is A, B, or C, and D, or E. But if you reduce this to a 2-level, distribute out distribute the C across the or here, you get AB plus CD plus CE. Right? Yeah. Which uses more gates. A, B, C, D, C, E. And then but you have a two-level implementation. Oh, I'm sorry, it uses the same number of gates. But this form will perform its operation faster because of the difference between having two-level here and a three-level here. So you want to strive for as few levels as possible. All right, so far we've been dealing with only and, or, and not. Which is all you really need when you, if you want to do basic digital logic, and I think in the lab that's all you use. That when you have two variables, you can have multiple functions. How many functions can you have? It's the last question on your homework assignment. The answer is 2 to the 2n. So if you have two variables, two literals, you can have 16 functions. Okay. Let's see here. Two functions produce a constant. Two functions. Produce 0 or 1. Four functions with unary operations, complement and transfer. Okay. And then 10 functions with binary operations that define 8 different operations. 10 functions, 8 operations. Those are the AND function, the OR function, the NAND function, NOR, exclusive OR, exclusive NOR, inhibition and implication. And implication. Okay. So we'll go through each one of these. Two functions produce 0 or 1. So that's A and B. So you have A and B out. And let's do the two functions produce 0 or 1. So one will be here. One function will just produce zeros regardless of the output or the input. That's effectively changing or connecting the output to ground. Likewise, you have the one function, the identity function, that produces a 1 regardless of the input. That's the same as connecting your output to the power line. Okay? And, or, NAND, NOR, and XOR, we've covered previously. You should know the state tables for those. Exclusive NOR is also called equivalence. Are the bits the same? So that would be XNOR. Inhibition, how does it describe it here? Inhibition is X but not Y. So X and not Y. So that's a 1 here and the A but not B. There's 2 inhibitions for A and not B, and the other one is B but not A. All right. Now, implication is the truth table for if-then, if you've had discrete structures already. It is the inverse of inhibition. A implies B would look like this, 1, 1, 0, 1. And B implies A would be 1 here. So there are 2 inhibition, or 2 inhibition and 2 implication functions. So all told, you can have 16 different functions with 2 variables. As you can see, 2 variables leaves 4 options. And if you have 4 options, the number of combinations accordingly is 2 to that power. So 2 to the 4th power would be 16. So in the end, you have a really large state table. And you have A, B, F1, 2, and F, yeah, function 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So A and B would be 0, 0, 0, 1, 1, 0, 1, 1. And yeah, it would be 0, 0, 0. Uh, let's see here. Okay, so your F0 is the null function. Function 1 is the AND function. Let's see here, that's A and B. Inhibition, X but not Y. It'd be X/Y. This is transfer, just A. And another inhibition, X but not, or Y but not X. So Y/X. Easier to do this with glasses on. Transfer. I'm sorry. B is A. B and A and A B. This is exclusive OR. A exclusive OR B. This is A or B. A nor B. Exclusive nor. A B complement. And or that would be equivalence as well is what it's called. Complement is here for B prime. Implication X. I'm sorry. A B. A looks like the subset symbol. Complement of A prime. This is B implies A, and then NAND A up arrow B, and then identity. And this is the null. Those are all the functions you can have with two variables. Adding a third variable would make it 2 to the 16th power, or 2 to the 6th power functions. Don't get into that, just deal with two functions at a time. Now, the thing with trying to implement these functions in circuits, let's see here, the only ones that are implemented in integrated circuits are the AND. You don't need the identity or transfer. That's just a line, but not the implications. The exclusive OR is NAND, NOR is. It's hard to find, but exclusive NOR is. Inverter is. Implication is not. Implication, oh, these are inhibition, are not. And then NAND is. And the identity is not needed. So the underlined functions, with the exception of with the exception of these two, B prime and A, are commutative. It doesn't matter which input goes where. I see a question rising on somebody's face. Okay. But those are all the possible functions that you can have, all the possible combinations of A and A prime and B prime in their respective functions. But only these are implemented in hardware. Because like here, A and B can't be swapped around. If you swap A and B around, you get a different function. So how would you wire that in an integrated circuit? So it's not used much. In the 7400 series, the NOR, exclusive NOR, is not implemented because you could just take an exclusive OR and put an inverter on it. and the exclusive NOR is not used very often in logic circuits. But any questions about these functions? I think we might just wrap it up for the day then. Yes. Yes, we do, next Wednesday. Yes. It'll be covering everything up to today. Yeah. There is no class on Friday, Mental Health Day. So you get Friday off. Wednesday we'll go over the homework and review for the any questions for the midterm. Yeah.
Actually, how many questions are on midterm?
Either 10 or 15. I haven't decided yet. Yeah. No. We're just doing review for the midterm on Monday. Yeah. Anything else? All right. Have a good day.